So, we are here in the third module of finite volume time domain lecture. So, we have seen so far the various dimensions of formulating the finite volume equations for Maxwell system, and also we discussed quite a lot about the discretization and the time discretization, to be specific, also on the spatial discretization. We discussed a lot about also advanced techniques. So, we are today going to follow up on the advanced techniques for domain truncation, and we are going to expand that to radial case and also spherical case, because so far we have been truncating domains on a rectangular manner. So, which is quite good for plane wave and also for, let us say, waveguide applications, but it is more convenient to go for radial or spherical domain truncation techniques. So, that is what we will be focusing today, and in the later stage we will also show some applications of finite volume time domain for practical problem solving, either in antennas or in waveguides, and also conclude this module on finite volume time domain, openly discussing about some of the challenges that this method is facing and what are the next further research that is needed, and also giving a kind of a direction for future research. With that, let us go into the today's lecture. So, we will start with the domain truncation technique 2, which I call 2 because we have started with domain truncation technique in the earlier modules. We will show some applications and some of the challenges. With that, let us begin with domain truncation part 2. If you remember, we had this equation that is coming from our system of equations of finite volume. Let us see this in the slide. We said that we can reuse the first flux directly computed from the first equation. So, irrespective of the fact that we have 4 equations, the last equations the flux value is recomputed, and the first 3 nothing but the standard finite volume time domain equation with PML losses, and the losses are given using the terms here, and these terms are going to be the losses in the x direction, because we were interested in truncating the domain for plane wave application or waveguide application along x axis. You can also notice that this 4th equation will have a loss term already sitting here, so it is going to be coupled as per the equation. So, that being said, let us go back to the slides. We said we will have the matrix material parameters given by alpha, which is here, as you can see in the slides, and these values are mu naught and epsilon naught accordingly, and the field vector, the combined field vector, is given by qi, which is hx, hy, ez and kx. We are talking about transverse magnetic case. The counterpart will be transverse electric case, where you will have ex, ey and hz, and accordingly the value, the 4th value will also change. So, we have the final form of the simplified equation, which is given by the final equation here. As you can see, this is semi discrete, it is continuous still in time, but we have already covered how to discretize the time variable. So, it is enough that we focus now on this one. So, this Li are these loss terms. Let me explain this further in the slide here. So, if you can see here, this Li terms are those loss terms. So, these terms are sitting here. So, it will be a vector whose first value, second value, third value are given by these equation, and the last value will be 0, because there is no losses here, the loss is already sitting here. And we discussed about alpha, which is given here, and Vi, as we already know in the finite volume formulation, will be the value of the volume of the cell. In the case of 2 dimension, this will be the area, and then we will have the surface or the counterpart of the 2D case with the length of the edges sitting here. So with this equation, we are able to understand that this is good enough for us to model plane wave, or also in the case of waveguide truncation. So let us look at in the case how we can expand this for a radial case, because what we are interested is we wanted to have a kind of a truncation, as we can see here. For example, we might have an antenna, and we do not want to truncate the antenna like this, because this way we are kind of, in one sense, we are increasing the surface that is needed to be meshed and computed. And secondly, in some cases the angle of incidence is quite close to normal, in some cases it is in grazing angles. As we already saw, the performance of the PML and also absorbing boundary conditions are good in the normal incidence case, but it deteriorates over when we go away from the normal incidence case. So this will something we wanted to see. So in this kind of case, what we want is, we want to truncate the antenna like this. So in the case of a rectangular truncation, we have to put the boundary conditions like this, but in the case of a radial truncation, our PML will be in this area. So this will be the PML area. In the case of radial truncation, in the case of rectangular domain, this will be the PML. And also we already saw that we need to have special conditions for the PML that are facing in the x direction and y direction and so on and so forth. So this is something we need to avoid. In the sense, what I wanted to say is, we need to have a general condition that is good enough for various angles of incidence, and also it is enabling us to model geometry in a compact way and also accurate way. So in that sense, going for rectangular truncation, you need to specify the way in which the PML will behave for x axis and y axis, and this is something that we can avoid if we go for a radial truncation. So this is what I am going to explain you in this class. This has certain advantages, as I already mentioned, in terms of formulation, but also it is good for numerical accuracy point of view also, because more or less we can come close to normal incidence if we are able to keep the domain in a way that we will see in the examples. So let us go into the theory of radial truncation. So right now we have got a simple condition where PML is sitting on the x axis. So the PML is actually an x oriented PML. So x axis oriented uniaxial PML. So what we want is, we wanted to have a PML that is radially oriented. So in that sense, regardless of which direction I am coming from, the anisotropy which we called, so let us go back. The anisotropy is in the epsilon by epsilon is equal to mu by mu. We said if it is a x oriented PML, we will have the anisotropy in this direction, and the rest of the, it is a diagonal matrix, and we will have 1 by a if it is an x oriented PML. So what we are trying to do is, we are trying to make sure that this one will be, the anisotropic direction will be, instead of x, it will be the radial direction. So instead of x, we are going into the radial direction. So that is what we are seeing here in the slides. If you see the xr, what we have in the rotated symmetry here is the direction in which the PML is going to be anisotropic, and we are moving from a, locally we are talking about a radial axis which is xr, yr and z. We have kept z here because we assume that along the z axis the PML is going to be symmetric, so we are not going to worry about the z axis. What we are interested is only the x and y axis. So globally we are sitting in x, y, z coordinate, and locally we are in the radial xr, yr. where XR and YR are actually defined using this particular transformation. So what we are going to get is a radial PML, radial uniaxial PML. Anisotropy is locally defined in the radial direction, as I mentioned here in this case, and the beauty is approximation is perfect at infinite PML radius of curvature, because when you are talking about infinite radius of curvature, we are basically talking about a plane PML, because radius of curvature we will see in the next slides. So if you can see here, so this is the way we define the radius of curvature. So if you have a PML like this, so this is the radius of curvature. So when R is tending to infinity, so this will become almost flat. So here R is moving to infinity. So this is the kind of transformation or approximation we are tending to. For most of the practical application, this approximation is good. So for most engineering application, which we will show in the next slides, this formulation has been good enough with respect to the absorbing boundary conditions that we have already discussed, like Sylvester or any of the other absorbing boundary conditions. And also this approximation is enabling us to come closer to measurement also. In the case of antenna chamber measurements and things of that sort, 40 dB, minus 40 dB or minus 50 dB is good enough, and for most applications this is the range we want it to be in. We can even go lower if we can reduce the spatial discretization. That means we are going finer and finer per wavelength, and also you can improve the accuracy by making the radius of curvature larger and larger. So we wanted to have a compromise. In the compromise, we wanted to make sure that the radius of curvature is small enough, at the same time large enough for most of the application. So we will have now the formulation for the uniaxial radial PML. We will begin with the equation which we are already familiar with, and we are going to take it forward to the radial case. So let me explain this, how we are doing it. So we are aware of this equation from our earlier slide. So we have here the material parameters, we have the loss terms and the flux terms. So what we are doing here is we are doing the rotation, as I explained to you in the earlier slides. So this rotation is going to impact only the x and y lying components. As you can see here, only the hx and hy and kx are going to be affected. Ez value will not be affected, because Ez is oriented in the z direction and there is symmetry in the z direction. We are not doing any transformation, so you will not have any impact on the Ez field. What you will have is only the variation in the hx and hy and kx fields. So what we have here as rotation is a simple transformation that is going to take each and every component in the hx hy area and going to transform it using the coefficient of the rotation, which is cos phi, sin phi, minus sin phi and cos phi. This is a simple rotational thing, and you will see that there is no influence on the Ez, because this will be the same. It's 1 here because Ez is not going to be affected. The kx, kxr are the quantities we are already computing, and we will have the values accordingly given by the last equation. As you can see, these are the initial terms. The main term that is going to impact in the radial PML are these kx terms. These are the terms that you have here. So these are already the original terms that we have got from the Maxwell equation for finite volume, but these terms are going to impact. And as I already told you, we are not going to do any additional computation, because this value is already coming from here and this value is already coming from here. One important thing to notice is, in the case of the planar PML, we didn't have two terms, we had only one terms. So maybe we can see this once more when we go back into the slides. and I can explain you this. In this case we do not have two terms, but we had only one term. We had only hx component for kx, but in the case of radial PML we not only have the hx component but also the hy, the flux of hy component, which is logical, but it is has to be seen also in terms of the value of phi, which is the rotational angles. As you can see here in the slide, there are two terms, but they are sitting in the case of hx it will be cos phi, and if it is hy it will be sin phi, and we will see in the next slide why this makes sense. And we will see that this is the loss term, which is also given by the earlier slides. So we will see here the loss term is given by kx values and hy values, and Ez value is already the same, and we do not have the last term like in the case of earlier uniaxial PML in x direction. We did not have any term on the fourth vector component. So that is the same way, and Ez component is the same. We see that we are only impacting the terms on the hx and hy, or the x, the main two components. We will see here why this makes sense. For example, if we put phi equal to 0 in this equation, so what we will see is all the components of sine will become 0 except for the component of cos phi, because cos phi will be 1. So we will have kx, and this is exactly the equation what we had for a uniaxial x oriented PML. So it gives us confidence that this formulation is correct for all the different combinations for the rotation. So if this is not correct when you put phi, then we have made some mistakes in the formulation, but once we put phi we are getting back to this equation. And also once phi is 0, as you can see here in the earlier slide, when phi is 0, this component, the y component, will become 0, but this component will be there, which is exactly the same as in the case of uniaxial x oriented PML. So putting things together, this makes sense. So now we are coming to unique properties of this PML. We said that we are able to extend the uniaxial PML oriented in the x direction to radial direction. We have got a nice formulation for it, and we wanted to see how much of this formulation can be practically used for problem solving. That being said, the advantage of this one is it gives us only one generalized formulation. So instead of taking a uniaxial in x direction, or uniaxial in y direction, or uniaxial in z direction, I can just live with one particular equation. Let me explain this with this slide here. So what I am talking about is, so in the case of Béranger PML, we said, which is the split case, we saw this also in our earlier lectures in finite difference and finite difference method and finite element method. So you have this is, let's say this is x and y, so this will be the x oriented, so this will be also x oriented, this will be y oriented, this will be also y oriented, but these corners are special cases. I think we saw this also in our earlier lectures in the finite difference method. So this one, this one, this one, and this one are special cases. So they have both x and y oriented. So we have to handle them specially, we have to have computed different fluxes. So this we can avoid when we go from the split formulation to uniaxial formulation. So what I am talking about is, regardless of what is my direction, if I have to truncate it, so I will call this one as my thickness, so thickness of my absorber, I will use the word D absorber. So normally what I will do is I will go for a thickness that is good enough for most practical applications. So, I will say I will go for 1 lambda minimum. So, whatever is my minimum wavelength, I will choose that it will be the thickness of my absorber, and I can say this is roughly in the case of most of the practical discretization level, we are talking about something around 15 layers of PML. So, when I say 15 layers, what I am talking about is 15 cells will be sitting. So, the number of triangles in each of the directions what we are talking about will be roughly 15. So, this is figure what we can use as a rule of thumb, and we can live with it because most of the applications we are talking about 10 to 15 cells. So, that is fine, and the beauty of this formulation is we do not need to have any special conditions, because we said this is our radial direction and it is uniaxial in radial direction. So, regardless of which direction I go, whether it is x axis or a y axis, and you will also see in the case when we are talking about a z axis, we can do the same thing also in the 3 dimension where the radial PML will be still valid. So, that being the case, we are able to formulate it in a much more easier manner, and what we get as advantages, we get one generalized formulation. This is something I already discussed right now for all regions, and we are able to say that geometry dependent terms are computed only once. So, most of the geometry dependent terms what we are talking about are the values of this phi and also the values of some of the material parameters and also the volume and the edge length and all this kind of things we are computing only once. So, we do not need to go to them, we do not need to compute them in each of the time loop. This is one good thing as well, and this is not particular to finite volume, this is generally the case. If you want to optimize your code, you have to make sure that you are computing the geometry dependent terms only once. The most important thing is we get one generalized formulation, and the lower number of update equations as we also discussed, we do not need to compute fluxes separately for the loss terms and also for the additional variable. This is already integrated in the earlier computations that we do, and there is a trade off. Everything does not come for free, there is a trade off. So, we will discuss what this trade off is in the next module. So, what we will see is how we can optimize this, what is the trade off we are talking about, what are the ways in which it will affect our numerical measurements, and how we can make sure that this is good enough for most of the applications. So, until then we leave here, and then we will come back and see the applications in the next module. Thank you.